pathway annotation. And to start right away, I want to give you this illustration about our workflow of the program. Pretty straightforward. What you need to provide is the gene set, what you want to have annotated, and a couple of pathways what you can obtain from KEC or GEO or wherever you want to look them up. And then what you also need to provide is a network like string or funcap. Because in our opinion, instead of like looking at the gene overlap, what most common tools do, you should like look at the interactions in a network on a global genomic scale to infer the enrichment of pathways. So in a first pre-processing step, what we are doing is evaluating the gene sets and the pathway pairs, what makes sense to get processed. It's just like to speed up things. And then the most important part is that we are taking the whole network and randomizing it like a couple of 100,000 times to get like a random statistical model. Because like in the main analysis part, we are then looking at each gene set and pathway pair and looking up in the real network how many interactions do we have, and then we are comparing it to like a random crosstalk distribution from the random networks, and then assuming that this is like binomial distributed, and then we can do simple alternative hypothesis testing and infer like a significance score out of that. So all what you get like afterwards out of Binox is like a huge Excel file or TSV file where you have then like the pathway gene set combinations and p-values, and we do multiple testing correction, and you get some further statistics as well. So what we can show, like if we compare to similar network-based approaches, Binox is outperforming them when it comes to computation time by far. It's like instead of waiting an hour for some analysis, you're just waiting a couple of minutes or a couple of seconds. This is very important, especially when you're working together with biologists, because they cannot wait for hours or days to get their gene sets annotated. Some further benchmarks on true positive rate and false positive rate, where we took like pathways and we tiered them apart, and then we tried, or the method should find them back together, and if they find the whole pathway back together, then we would count it as a true positive. Whereas if we look at false positive, there we just replaced in the halves the genes with random genes, and if the methods would report an enrichment there, then we would count this as a false positive. And we can see that Binox is like having a really high true positive rate while keeping a really low false positive rate. And whereas like the other methods have either a high true positive rate with a lot of coverage and a really high false positive rate as well, or a low false positive rate, and then they are suffering of not having enough coverage. What we also noticed while benchmarking is that the methods seem to act differently when you're looking at really small pathways. That's why we only looked at the smallest 25% as well, and we basically saw that Binox is having like the same performance, whereas the other methods really drop in coverage or have an increased false positive rate, which we should not recommend to use for further analysis of your gene sets. Finally, we wrapped up the program in a web service, which you can find on the PATHWAX.SBC.SU.SE. There, we already randomized the networks for a couple of species, 1,000 of times. And all you need to provide is like a list of gene names, and then it will analyze you your gene set basically in a few seconds to minutes, and you will be further redirected. What you will get in the end is like something what you can see here with the pathways, the FDR score, and which genes are in the pathway, and in your gene signature you can apply different filters and thresholds, and you can find more information about our papers, about PATHWAX and about Binox. Yeah, thank you very much.